All right. So what happens if we have multiple capacitors? If we have multiple capacitors, then there are basically two kind of structures that are often seen in the circuit. One is a capacitors in series, which means a capacitor are connected one to each other, like head-to-toe structure. And another one is called capacitors in parallel, which means all the capacitors, one end of them, they share the same head, and another end share the same toe. So how do we analyze such a multiple capacitor circuit? So first, let's take a look at a capacitor in series. Before you just look into this answer, let me guide you through this logic and how you will understand this relationship. So first, if we have a capacitor, we have a battery. The battery is connected to different capacitors. So we can compare the relationship between charges, voltage, and maybe construct its equivalent capacitance. So let's think about the charge first. So when I put this 3 and connect it to the battery, this battery will send a charge Q here, send a negative charge Q here. And because of the electric force, right, this positive charge will attract. So you can think about this area. Even though it's a wire plate structure, but really they're all conductor, right? So you can imagine this is just one conductor. If I put some positive charge here, what's gonna happen on this conductor? It's gonna have a charge separation because the positive charge will attract all the negative charge, like toward to it, and they push all the same type of charge away from it. So eventually, this positive charge, the top plate, it will attract all the negative charge, the equal amount of negative charge towards to it. So you have positive charge on this plate and negative charge on that plate. Okay. So this is because of the attraction. So this is about attraction. And how about next? Remember we said this wire plate, you can see this guy hold all together. It was neutral, right? It was a neutral conductor. Now if I have all the negative charge on one end, then the other end will be filled with positive charges because this guy was neutral before. One is positive, one is negative because the charge has to be the same. It has to be neutral. Like originally, this entire conductor was neutral. And then so on and so forth. Once all the positive charge are on this plate, this positive charge will attract the negative charge from the another end. So it will attract all the negative charge here. And since all the negative charge is attracted upward, then all the positive charge must be pushed downward and stored on this plate. And this is positive charges and this negative charge, of course, they will naturally attract to each other, so they are happy. So eventually, because of this logic, one by one, you can see the charge stored on the first. You can see that the charge is stored on the first capacitor. Let me give you a new color. Let's do orange. I like orange. This charge, the charge held by this first capacitor, we call it Q1. The charge held by the second capacitor, we call it Q2. And the third one, we call it Q3. You can see that they all share the same charge. And if we want to find equivalent resistance, a resistor to represent the entire, all of them, then this one must share the same charge as well. This charge, because it's connected to the battery, we want to make sure like outside of it, it should all look the same. So the charge must be the same as well. It will be the same as the top charge and the lower charge. And then we can come back to see the voltage. the battery will provide a voltage V. And you can see this voltage will drop across this one, drop again across this one, and drop again across that one. And eventually it will lose all of its energy and then come back to this battery. So the voltage of the battery equals to the sum of all the individual voltage. And thus the voltage of battery is also the voltage that apply on the equivalent resistance. So based on these two relations, now we can derive the relationship between C1, C2, C3 with the effective resistance. So first we now remember C equals to Q over V. So I'm gonna apply this relation, combine this one and say, let's start from and plug this into this relation. So since total V equals to V1 plus V2 plus V3, and from this relation, we know V equals to Q over C if you swap these two places. And then you get V, this V, if you look at the lower picture, this V, the voltage of a battery is the Q, the charge over the effective resistance, effective capacitance equals to V1. So V1 will be Q1 over C1 and plus V2. V2 is Q2 over C2, so on and so forth. And since the Q are the same for Q1, Q2, Q3, and the total charge for the effective capacitance, then since they all share the same charge, so this charge can be canceled out, then eventually you will arrive with this relation. So this is a simple relation that will tell you if I have multiple capacitors connected in series, the effective capacitance in this case will be the sum of the inverse of them and then inverse again. All right. So this is a capacitor in series, and we can take a look at the capacitor in parallel. The capacitor in parallel, let's see. This is C1, C2, and C3. Now this battery will send out the current and charge this 3 capacitor, right? In this case, it's probably easier to talk about the voltage first. The voltage, because they are all connected, 4 of them, they are connected in parallel. They all share the same potential here, and they all share the same potential on the other side. So V1, V2, V3, they will all have the same voltage. And this is exactly the voltage provided by the battery, because you can see the battery share the same toes and the same head. So the voltage are going to be the same for everyone. So how about charge? Now these 3, they are separated. They will not affect each other like they did in the series case. So basically, how much charge can be held on each capacitor just depend on the capacitance for them. So this one can probably hold a charge Q1. This one can hold charge Q2. This one can hold charge Q3. So the total amount of charge, if we model this case with the effective resistance, the total, and you can imagine because it's all wire, look at the wire and the metal, they are all conductor. So you can kind of reshape it and make it a huge capacitance. So the total charge, so you can see the total charge provided by this battery will be the sum of all the individual charges on each capacitor. Okay, so if the first capacitor get Q1, second one get Q2, the third one get Q3, and if you want to use an effective resistance to represent the 3, that resistor must be able to hold a charge as the sum of all of them. So now I understand how this individual voltage and individual charges and the relationship between total voltage and the total charges. once I understand this two, then I can use these two information to derive what kind of capacitance I need to make this to represent this whole thing. So my thought logic is the same. I want to use this relation C equals to Q over V, and combining this relation with this one. Since I know Q equals to Q1 plus Q2 plus Q3, and I also from this relation, I know Q equals to CV. So Q will be, so the Q, the total charge will be the C, the capacitance of the effective capacitance times the voltage, equals to Q1. Q1 will be C1 V1, and Q2 will be C2 V2, Q3 is C3 V3. But since V1, V2, V3, they are nothing but V, so I can replace V1, V2, V3 with V, and then I will have V everywhere, then I can cancel them out. So eventually I arrive with this relation where the effective resistance in this case will be the sum of individual capacitance. Let me clear the drawing. All right. I would highly recommend you go back and think about the relationship between them by yourself, because it's a little bit non-trivial in this case compared to the resistor. And you can see the result is the opposite.